Titrations with polyprotic acids are very similar to titrations with monoprotic acids, except for now we're dealing with neutralizing a second proton. So if you were to consider a monoprotic acid, we know that its titration curve looks something like this. And we can find the equivalence point, and we can do something similar with a polyprotic acid, but instead of just having one proton that we're neutralizing, now we have two. So the curve is going to look something like this. And we're going to actually end up having two equivalence points. So for this example, what we're going to do is we're going to look at some generic acid right here, polyprotic acid, and then these are the Ka values that we will use. So I'm going to assume that I have 100 milliliters of this 0.1 molar polyprotic acid, and again the Ka values, Ka1 and Ka2 are what I gave you previously. And what we want to do is we want to go through and calculate the pH along different steps in this titration. So the first thing we want to do is calculate the pH before any addition of sodium hydroxide. So here, since it is not technically a strong acid, since I give you Ka1, you just set up your dissociation reaction like so. And this should be very familiar by this point in time. And then you could go on and set up your ice chart. Okay, so then what happens is we can go through and use Ka1 to solve for x. So Ka1 is equal to 4.6 times 10 to the negative third. And then from our expression, this will be equal to x squared. So from these two components over 0.100 minus x. What happens is whenever we solve for x, we find that x is equal to 0.0193 molar. And so I'm actually not going to set up the reaction for Ka2 where we would have Ha plus H2O yielding H3O plus A2 minus. And the reason why is if you notice that X here is on the order of magnitude 10 to the negative second, and for Ka2, this is 10 to the negative 10th. So whenever we would go through and solve for x, what we'll see is it won't have an appreciable impact on the x, which is our concentration of hydronium. So we can just use this to calculate the pH. So here what we'll do is we know, again, that pH is equal to negative log of H3O plus concentration. So we can plug in x here. So then our pH is equal to 1.72. So let's keep marching along. So now we'll actually have added some hydroxide. So we are going to look at calculating the pH at halfway to the first equivalence point. So what we'll have to do is remember whenever we start neutralizing an acid or a base, we set up our reaction and we use an ice chart, but now we use moles instead of molarity. So we end up with this reaction. Polyprotic acid plus hydroxide yields Ha minus plus H2O. Going through and calculating the initial number of moles. So remember that you can do this because we know the volume and we know the molarity. Molarity is equal to moles over volume. So we can say that moles is equal to molarity times volume, where the volume has to be in liters. So here we've added 50 milliliters of hydroxide, which is 0.00500 moles. So then we will subtract off the smaller amount. Add this over here to our conjugate base. Made a mistake here. This should be 0.0050. So at the end, what we should have is we're left with half of our initial amount of strong acid, or sorry, our polyprotic acid. We don't have any hydroxide remaining. And then now we're going to be ready to set up our second ice chart. So here, the total volume, because we have to keep in mind the total volume whenever we start using KAs, because that's based off of concentrations, not moles. So this will be 150 milliliters. So now we're going to have to go through and set up another ice chart. But here, the slight difference is that we have an initial concentration of H2A and also HA minus. So whenever we plug in, we have to calculate the concentrations, which we'll get from these moles divided by this in liters. So that comes out to be 0.033 molar. Change will be minus X plus X plus X. Okay, so now we can use Ka1, where Ka1 is equal to 4.6 times 10 to the negative third. We can plug in our values. So our products go in the numerator, so we have X times 0.033 plus X divided by 0.033 minus X. Now from here we can go through and solve for X. And X is equal to 0.00368 molar. Then in a similar way to our logic for the first reaction is if you were to consider Ka2, which we would say we would have HA minus plus H2O yielding H3O plus A2 minus. We can go through and plug in X as our initial concentration of hydronium. And we could calculate the initial concentration from this to plug in over here for HA minus. But then at the end, whenever we start trying to calculate X for the second reaction with Ka2, since Ka2 is 2 times 10 to the negative 10th, the order of magnitude differs by 7 orders compared to our hydronium concentration. So we can go ahead and justify to leave that out. So we can calculate pH based off of this value that we found for X. So pH is equal to negative log of H3O plus. So we'll substitute this value in right here. So pH here at halfway to the first equivalence point is 2.4. All right, so let's keep going. So now we're going to get to the first equivalence point. And so again, these titrations, especially with polyprotic acids, there's a lot of steps, but the logic behind it is the exact same as just a monoprotic acid. So here, what we'll have is we can go ahead and write out our first ice chart. So we have H2A reacting with hydroxide. Going on to form HA minus plus H2O. So now we have the exact same molar amounts. So 0.0100 moles. 0.0100 moles initially. We'll subtract that off because we're at the equivalence point where the moles of the acid and the moles of the base are equal. And so what we'll end up left with, none of this remains, and all we have is 0.0100 moles of HA minus. And now our total volume is up to 200 milliliters. So from here, what we're going to do is we're going to have to set up an ice chart with HA minus. So we need to calculate that concentration. So let's go ahead and start by writing out our reaction. We have HA minus plus H2O yields H3O plus A2 minus. So whenever we calculate this concentration out, it is 0.0500 molar. We have minus x plus x plus x over here. So we'll have 0.0500 minus x, x and x. So now we're going to use Ka2. We're done with Ka1 because we're at the first equivalence point. So we no longer have any of this polyprotic acid left. So now we just have the HA minus. So we can use Ka2, which is 2.0 times 10 to the negative 10th, which is equal to x squared over 0.0500 minus x. Solving for x, we get 3.16 times 10 to the negative 6th molar. Again, we know that pH is equal to negative log of H3O plus. So we'll substitute in and we'll find that the pH at the first equivalence point is 5.5. So if you were to think about that generic titration curve that we have, so first we looked at the initial pH, which was right here. Then we did halfway to the equivalence point. We did the equivalence point. So now we're going to look at halfway between the first and second equivalence points here. And then we'll also look at the second equivalence point. So halfway between the first and second equivalence points, you have to take note now that all of the H2A has been consumed. So any additional hydroxide added beyond that 100 milliliters that neutralize H2A is what we're going to be comparing to the HA minus. So if you take note really quick, this is what our initial moles of HA minus will be. And then anything beyond the 100 milliliters of the sodium hydroxide is now what we're looking at. So now what we're looking at is halfway between the first and second equivalence points. So now we're at 150 milliliters of sodium hydroxide. So we're going to look at this reaction. We have HA minus plus OH minus yields A2 minus plus H2O. Like I said, the initial number of moles here is 0.0100 moles. And so now we're looking at, essentially we're looking at 50 milliliters of sodium hydroxide because the first 100 went to neutralizing completely the H2A. So now we have 0.0050 moles of hydroxide. So the change is minus 0.0050. We had no A2 minus initially present. So at equilibrium, we have 0.0050 moles of HA minus, no hydroxide remaining, and 0.0050 moles of A2 minus. And now our total volume is the sum of the 100 milliliters initially present of H2A plus the 150 milliliters of sodium hydroxide So we're up to 250 milliliters. So we can go ahead and set up our ice chart. So we'll have HA minus plus H2O yields A2 minus plus H3O plus. So now we're going to calculate the concentration from these moles and the volume. So we have 0.0200 molar. We have minus X plus X plus X. Okay, so we can plug in with Ka2, which we know is 2.0 times 10 to the negative 10th. It's equal to X times 0.0200 plus X, all divided by the quantity of 0.0200 minus X. So one of the things we can take note of really quick is notice that Ka2 is on the order of magnitude 10 to the negative second, and our concentration, 10 to the negative 10th. And then our concentrations here are on the order of magnitude of 10 to the negative second. So that means this X can fall out, and this will cancel. So X is actually equal to Ka2. And we can calculate our pH from this. So pH is equal to 9.70. And so now we're going to look at our final step, which will be at the second equivalence point. All right, so at our second equivalence point, what's happened so far is we've neutralized all the H2A, and now we will have neutralized all of the HA minus. So I'll go ahead and set up our reaction. We have HA minus plus OH minus yielding A2 minus plus H2O, and our initial moles 0.0100 moles. Same thing for hydroxide, because now we're only looking at the additional 100 milliliters that was added. Okay, so now we'll subtract off. So the only thing we're left here is that conjugate base A2 minus. So at equilibrium, no HA minus, no hydroxide, we have A2 minus. We need to take into account the total volume, so the 100 milliliters plus the 200 milliliters is a grand total of 300 milliliters. So now, what we're going to do is keep in mind, we know what Ka2 is. We know Ka2 is 2 times 10 to the negative 10th. But we don't have any acid left. We don't have any HA minus. So we actually need to recall that Kw is equal to Ka times Kb. So we will find Kb for this reaction, so for that conjugate base A2 minus. So Kb is equal to 5.0 times 10 to the negative fifth. And now we can use this for the following reaction. We can start off with A2 minus plus H2O yields conjugate acid plus hydroxide. So we can calculate the concentration of A2 minus from this moles and then convert our volume to liters. So we're at 0.033 no conjugate acid, no hydroxide. So the change is minus x plus x. So at equilibrium we have 0.033 minus x, x. So we can use Kb to calculate this. So Kb for our second reaction is equal to 5.0 times 10 to the negative fifth, which is equal to x squared over 0.033 minus x. Solving for x gives us 0.00126 molar. And what we'll see now is x is equal to the concentration of OH minus. So we can substitute in, and we can find that POH is equal to 2.9, which means that the pH is equal to 11.1. So this is the last step, once you get to the second equivalence point or beyond, where things start to get tricky. And this is just like a monoprotic titration. Whenever you've used up all the acid and all you have left is base, you may have to turn around and find Kb or Ka, depending on what kind of titration it is. So I hope this helps with the polyprotic acid titrations, and next time we'll start to look at some solubility equilibria.